For many decades, computing power has followed a surprisingly predictable trend, one predicted by Gordon Moore, co-founder of Intel. Moore's law is the observation that the number of transistors on a microchip doubles approximately every 2 years, leading to exponential growth in processing power. This prediction has held true for decades, driving faster and more efficient computers. This increase in the number of transistors on a chip has been accompanied by a similar exponential increase in performance. Unfortunately, this trend has started to hit some limits in recent decades, with the trend starting to plateau. But even in these recent decades with much slower performance gains, what are all these additional transistors actually being used for, if not improving the performance of the chip? Well, the answer is that microprocessor manufacturers are now creating chips containing multiple individual processing cores on a single die. Having multiple cores allows a chip to work in parallel, which can massively speed up many workloads encountered in the modern day. Even many consumer chips now have many individual cores. This provides a huge opportunity to the programmers who are able to effectively take advantage of this additional power. Being able to write parallel code has increasingly become an essential skill for programmers, as this is the main way that we're able to access more and more computational power. In this video, we'll start exploring some of the theory behind parallel programming and lay the groundwork for how to practically take advantage of this additional computational power that is often left unharnessed. Let's get started. Instead of just jumping into an abstract algorithm, I want to start by looking at a simple real-world issue of managing a kitchen. In this simple example, these chefs or workers will be an analogy for our CPU processing cores. Our goal for this example is to manage the production of a cheese and tomato sandwich. In this process, there are several steps. The first step is to cut the tomatoes, the second step is to cut some cheese, third step butter bread. In the fourth step, we assemble all of these ingredients into a sandwich, and in the final step, we cut the sandwich and serve it to a customer. If we only have one chef, this chef can just follow this recipe in order to produce the sandwich. But what if we wanted to actually optimize this process to try and produce the sandwich as quickly as possible? One option we have is to hire more chefs to work on sandwich production, but this will require us to actually split the workload amongst the chefs. If we now have 3 chefs, we could, for example, assign the first one to cut tomatoes while the second one is buttering bread. However, if we were to assign the third to assemble the sandwich, we'd run into an issue. You can't assemble the sandwich before the ingredients have been prepared. In this example, there's an obvious dependency on the first 3 tasks, A, B, and C, being completed before we can start working on task D. When we have these dependencies involved, it's often helpful to arrange our tasks in a dependency graph. In particular, this type of graph is a directed acyclic graph, or DAG for short. The edges in this graph indicate dependencies. So for example, you must butter the bread before assembling the sandwich. For a dependency graph to make any sense, there can't be any cycles in this graph, because this wouldn't make sense for a well-defined algorithm. Now you might be asking yourself, why do we even bother with this view? Well, this type of graph allows us to explicitly view the dependencies between tasks and work out how we can distribute them amongst our chefs. This dependency graph gives us 2 very important pieces of information. For each task, we know which other dependencies need to be completed first before we can begin executing that task. But what it also tells us is that tasks that don't depend on one another can be worked on at the same time. And this is a main concept behind parallel programming. If 2 tasks don't depend on each other, you can work on them at the same time. This simple concept of dependencies dictating what can be done in parallel is really a fundamental part of parallel computing, and it's very critical to understand. Whether you're only using multiple cores on your local computer, or you're trying to scale a program across an entire computing cluster. Going back to our kitchen example, you can have one person cutting the tomatoes while the other person cuts the cheese, and yet a third person butters the bread. However, all of these tasks need to be completed before the sandwich can be assembled. And once the sandwich has been assembled, you can then go on to cut the sandwich and serve it to a customer. So now we've got an idea of how to structure our parallel algorithm, by which we mean how to schedule our tasks. So now let's try and compare our 2 processes, one using 3 chefs and one using a single chef. In order to be able to do this comparison effectively, we need to assign some numbers to each task, and we'll make the assumption that all of our chefs are equally skilled and can complete each task as fast as the others. So in our example, we'll take 70 seconds to cut the tomatoes, 80 seconds for the cheese, 50 seconds for the bread, and 20 seconds each for assembly and serving. And one thing to notice from our DAG is that we can identify a maximum critical path, which has a total time of 2 minutes. This means that no matter how many workers we have for this process, we can only possibly complete the process in 2 minutes. In fact, if we have more than 3 chefs, we won't be able to assign them any additional work to try and speed up this process anymore. With our 3 workers, we can achieve the minimum execution time of 2 minutes. And this is a 2 times improvement over the original 4 minutes that it would take a single chef to produce the sandwich. But since we needed 3 workers to achieve this 2 times speedup, we say that this assignment has an efficiency of around 67%. Having an efficiency lower than 100% indicates that some of our assigned workers are just waiting around for some portion of our execution time and not actually contributing to reducing our runtime. This idea of efficiency is very important to understand and is particularly useful to consider when you're allocating limited resources, for example on a computing cluster. If the efficiency is low for an algorithm, parallel processing is unlikely to help. Fortunately, there's a theoretical law for parallel processing which helps us to understand how suitable an algorithm is for parallelization, and if suitable, how many workers we can use to efficiently speed up our algorithm. What we're talking about is Amdahl's law, which follows this formula, which tells you the theoretical maximum speedup a program can possibly achieve, given that a portion of the code P can be parallelized. This means that 1 minus P represents the proportion of time in the algorithm that must be done sequentially. In this example, I've made the simplifying assumption that the speedup of the parallel portion of the code is directly equal to the number of workers assigned to this problem. In general, when you see Amdahl's law being written online, you'll see this factor being S instead of N, where S stands for the parallel speedup that you're likely to achieve on the parallel portion of your code. Since this S is limited by the number of workers that you're using N instead of S still provides a useful upper bound for our estimate, and so we'll keep our formula in terms of N instead of S. So let's have a look at our speedup for a perfectly parallelizable workload with P equal to 1. This curve is actually quite boring, and it's what most people expect when you parallelize an algorithm. So what you're seeing is for 16 workers, you expect to see a 16 times speedup. In reality, this is really the best case scenario when it comes to parallel computing. So now if we reduce P by just 1% and plot the curve again, you can see that this small change has a huge effect on how much we can speed up our code. Now when we're using 16 workers, we can only achieve a maximum speedup of just under 14 times. Dropping P to 80% means that now with 16 workers, we can only possibly achieve a speedup of 4 times. This means our efficiency has dropped to only 25%, even though only 20% of our code actually had a serial dependency, and 80% of it could be parallelized. For a final example, we can see that if only half the code can be parallelized, even with an infinite amount of workers, you can only hope to achieve a 2 times speedup. While Amdahl's law is just a theoretical framework for understanding parallelization, we can see a few things. The first is that if the parallel proportion P is quite low, this will dramatically reduce the possible speedup of your code if you're going to parallelize it. So not only is your speedup limited to the number of workers that you have available, but your algorithm will also impose hard limits on how much speedup you can hope to achieve. This means that Amdahl's law is actually very pessimistic for parallel programming, because it shows that it's usually only worth parallelizing algorithms with a very high value of P. Worse still is that this speedup is only a theoretical maximum. Often this maximum is actually rarely achievable in practice. But there is one saving grace. Many problems for which we use parallel computing usually have a value of P which grows with the problem size. This means as the workload size increases, parallel programming becomes more and more efficient, and these workloads become more and more suitable for parallelization. If you're interested in reading the theoretical grounding for this, I would suggest looking up Gustafson's law. For now, let's leave this theory behind and look at 2 very common patterns that lend themselves to parallelization that you might see dotted around your codebase. The first of these operations represents the very best case scenario for parallel computing, and this is the map operation. This type of operation is very simple to implement using parallel computing and is often referred to as an embarrassingly parallel algorithm. I'm almost certain that you will have used this type of operation before in your code at some point. In particular, you're very likely to have used a map operation when you're plotting a graph. When you're using a plotting library, you have to create an array which represents a discretization of the function that you want to plot. In particular, if you're plotting a 2D function, you'll have to perform a map from a range of x values to a range of y values, which is what gets displayed on your screen. Now, this operation is usually implemented with a simple for loop, with each element of the output array being calculated sequentially. But since the calculation of each point doesn't depend on any other points, we're free to calculate each of these points in parallel. Ideally, this means that if we have as many workers as we have points to calculate, we can calculate all of these points in the same amount of time as it takes to calculate a single point. Even when you have fewer workers than points, it's usually possible to achieve close to 100% efficiency on this type of operation. So to continue looking at this map operation, let's look at an even simpler example of just trying to double each element in an array. It's easy to see why this operation is so parallelizable. The DAG for this operation is very simple. Each output has a single dependency on one input value. Since there are no shared dependencies, this is perfectly parallelizable. In general, this type of map operation has a complexity of big O of the ceiling of n divided by w, where n is the number of items in the map and w is the number of workers used. Another pattern that you'll often see is a reduction. This is where you're combining multiple entries together to produce an output with fewer elements than you started with. The most typical form of a reduction is reducing a vector of elements into a single element. You typically use reductions to calculate averages or sums over a batch of values. To look at a particular example, let's see how we can use a reduction to calculate the area under a curve. If we're doing this numerically, what we would do is first calculate the heights of various points along a curve. We can then use these heights to calculate the area of trapeziums, and then sequentially add these areas together into a variable which keeps track of the total sum. We would call this operation a reduction because we're effectively turning a vector of areas of trapeziums into a single number, which is the total area. In order to better parallelize this, what we can do is pair off each trapezium with its neighbor. Each one of these pairs can be added up independently and so can be parallelized across a set of workers. And so the first step in this reduction would involve combining each pair of trapeziums. So if we started with 8 areas, we're now left with only 4 areas. We can apply this process again, which will turn our 4 areas into only 2 areas. We have to perform this operation yet one more time to combine the final 2 areas into 1 area. So let's look at the same algorithm in a different context, so that we can explicitly visualize the underlying DAG. In this example, we're just adding up all of the numbers in an array. In the first step of this process, we pair off each of the adjacent elements and add each of these pairs together. This first step can be done with 4 workers. However, all workers have to finish executing before the next stage can continue. In the next step, we can only perform 2 of the operations in parallel. And so if we assigned 4 workers to this problem, 2 of them would be sitting idle for this stage. The next and final step can only be done by a single worker, which would leave 3 workers sitting idle. But once we're done with this stage, we have our final result. In general, the number of steps in this reduction is proportional to the log of the number of elements in your list. So this reduction is still quite efficient to run in a parallel fashion when you have lots of processes that can be efficiently synchronized to work together. And that's because the serial equivalent runs in O of n time. But in theory, we could reduce this runtime to O of log n instead. And if we remember back to our computational complexity video, O of log n has much better scaling than linear. Unfortunately, achieving log n runtime is often unrealistic for implementations of this algorithm, but we'll talk about this in more detail later on in the series. The reason why we covered these 2 types of operations is that many algorithms that are suitable for parallelization can be broken down into sequences of map and reduce operations. So now to see this more clearly, let's look at an example workload which we can use to view these map and reduce operations in action. The algorithm that we'll look at is a Monte-Carlo based algorithm for estimating pi. We're looking at this example in particular because Monte-Carlo algorithms are incredibly common methods that are used across a variety of fields in science. This algorithm works by throwing virtual darts at a dartboard. As the computer is not a very good darts player, each dart uniformly, randomly hits anywhere within the square region, and sometimes misses the dartboard completely. Given this distribution, we know that the proportion of hits within the circle is proportional to pi. This means that if we count the number of hits within the circle and the number of darts thrown, we can directly estimate pi using this formula on screen. Each new dart that the computer throws makes our estimate for pi more and more accurate. We usually need to simulate many of these darts being thrown in order to get a reasonably accurate value for pi. So now that you understand the problem, let's see how we can view this as a map-reduce problem. Each time we throw a dart, we can imagine that we are mapping the dart directly into a number, either 0 or 1. 0 for a miss and 1 for a hit. Once we've mapped this array, we can perform a final reduction which adds up all of the 0s and 1s into a final number. This is equivalent to counting the number of hits, whose final result can be directly used for our final estimate of pi. So now that we understand the basic building blocks, let's take a look at an example implementation in Julia. In this source code, we're defining one function which throws a virtual dart and returns a boolean to represent the hit or miss of this dart. This boolean can be implicitly converted to the 0 and 1 that we need for our numerical interpretation. Using this function, we can define a second function which performs our Monte-Carlo simulation. The simulation can be implemented using a map-reduce operation. But instead of breaking these operations into 2 stages, we can use a single function, map-reduce, which combines these 2 operations, providing a slightly more efficient implementation. The map-reduce function is a standard implementation given within the Julia base library. The first input argument defines the function that will be used for the mapping. In this case, we're mapping from the dart ID into whether that dart hit or missed the dartboard, and we define this using an anonymous function. The second argument defines the reduction operation. In this case, we'll just be adding up the number of hits, so we can simply pass in the addition operation. The last positional argument specifies the array that we perform the map over. This syntax just specifies a Julia range from 1 to n inclusive, where n is just the number of darts. Finally, this code specifies an initial starting value of 0 for the reduction, but this isn't strictly necessary, it's just good practice. While this implementation is relatively straightforward and works as expected, this video isn't about Monte-Carlo algorithms. Instead, we need to ask how we can run this algorithm in parallel. Well, in fact, this is actually very easy to do in Julia. And we can make use of an external package called threads.x, which provides several common parallel versions of functions like map and reduce. These implementations will perform the equivalent operations, but parallelized to make use of multiple cores on your system. So in order to create a parallel version of our simulation, we can simply use the map reduce function from the threads.x package, and we can keep the rest of the implementation exactly the same. So one useful thing that we can do now that we have these two different implementations is run benchmarks for various values of n to see what speedup we're able to achieve in practice. Timing the serial version of the code produces a predictable linear dependence on the number of darts used in the estimate. Now if we add in the benchmark for the threads.x version, what do you think the results should look like? Well, after adding in these parallel results, you see something rather interesting. For lower values of n, our parallel implementation was actually a lot slower than the original implementation. In fact, for n equals 10, the parallel implementation is around 100 times slower than the serial implementation. This is not really the result people expect when they start to parallelize their code. Why is the parallel implementation so much slower? The main reason for this drop in performance is due to overhead and synchronization costs. It takes time and resources to try and coordinate the execution of our parallel algorithm across several CPU cores. The time taken to orchestrate your parallel algorithm can actually dominate the runtime if the workloads are small enough. You can see that we have to make the workload much bigger to be able to start seeing the benefits of parallelizing our code. Only when we get to using more than around 10,000 darts do we begin to see any amount of improvement. In order to look at this data in a slightly clearer way, let's instead plot the speedup of our parallel code versus our serial code. Here we're plotting the time taken for each n divided by the time taken for the serial version, for the same number of darts. This view of the benchmark abstracts away the computational complexity of the algorithm and lets us focus just on the efficiency of our implementation. In this graph, you can see that the speedup is much less than 1 until n reaches around 10 to the 4. After this point, the speedup increases to a plateau which levels off at just under 7, which falls just shy of the expected maximum of 8. In this case, we expected a maximum of 8 times increase because we told Julia to use a maximum of 8 workers. Now for changing one line of code, this is a pretty good speedup, even if it falls short of this maximum efficiency. We'll revisit this example in later videos to see if we can match the performance of threads.x and try to exceed it using our own parallel implementations. For now, let's do a quick recap of what we've learned this session. The first key takeaway that I want you to have after this session is that what can be parallelized is dictated by dependency graphs. Tasks that are independent can be done in parallel. The second fact that we covered is that parallelization has theoretical limits on the speedup that you can possibly achieve, which is dependent on the number of workers that you use and the specific workload that you're trying to parallelize. And from the third example, you can see that the practicalities of parallelizing your code mean that it's actually quite difficult to achieve these theoretical limits. In the next few videos, we'll be exploring this concept in much greater detail, and we'll also introduce the 3 main paradigms for implementing parallel algorithms. You've already seen the first of these paradigms in this video, when we used the threads.x package. This paradigm is called multithreading, and it's one of the most accessible ways that you can add parallelism into your code. In a later video, we'll also introduce multiprocessing, which lets you take advantage of the computational power of an entire supercomputing cluster. In the last part of this series, we'll also talk about GPU programming, and GPUs are devices that are specifically designed for massively parallel execution, and they are the physical driving force behind the current AI revolution.